Now we've got Peter. Peter is a senior software engineer at Jump Trading's core engineering division, focusing on the Linux kernel and device driver development and embedded systems. Today, Peter will discuss the changes being made to the Linux kernel to handle hardware interrupts on non-traditional hardware.
Thank you very much. Can you guys hear me okay? Yep. All right. So, like you said, I wanted to give this talk today to talk about interrupt balancing. It's something that I do kind of outside of my day job for fun. And there have been some changes since the last time I talked about it in New Zealand, particularly around changes that ARM and RISC-V and some other architectures have been driving. So first and foremost, I am not going to attempt to pronounce the names because I don't want to offend anyone, but I did want to acknowledge the native folks in this land and want to extend that respect. And I also would really like to mention the Everything Open 2023 conference, the organizers, the volunteers, everyone that's working to bring this back. Just like it was mentioned this morning, it's really exciting to be back in person and actually see people in person, get to talk to people, have people throw questions at me that I don't know how to answer. So it's really, really nice to be back in person. And it's also a really big honor for the program committee to have invited me to come and speak. So thank you very much to all of you who made this go and hopefully make this go well for the rest of the time. All right, so first and foremost, why do I hope that you're here? So hopefully that first bullet, you do know that this is the interrupt balancing talk, right? So hopefully it is, what is interrupt balancing? Why is it important? Why is it something that we have something that does this in Linux systems? And also get some background as to why has this only been typically an x86 focus? Right, it's really been something that has targeted those systems. It really hasn't been either a thought for other architectures or a need. And if that was still the same case today, then I wouldn't be here talking to you about this. So, and so yeah, understanding why some of these other instruction set architectures are driving changes and kind of causing some issues that have to be addressed in order to make this a more robust subsystem. And I figured a really good place to start is, like I'd mentioned, at LCA 2019, I gave a talk on what exactly is interrupt balancing. So it was called Demystifying Interrupt Balancing. So I wanted to kind of recap a little bit just so that people are kind of up to speed as to what exactly is this thing, how does it work. But it'll be a very condensed version. I do have a link in the end of this presentation to that talk in case you are interested in actually knowing a little bit more about that. So, and then I wanted to kind of end with what does our current roadmap look like in the interrupt balancing space? You know, we do have some other things that are still on the roadmap to finish. I'm sure that that will change as more and more platforms come online, but we'll get to that in a little bit. I also wanted to mention we'll try to encourage questions to be at the end, just so that we can get the microphone around. But if there is something that I talk about that you have no idea what I said, I'd rather you guys let me know so I can address it. Please feel free to shout the question out. I'll try to repeat it. Because if you don't know something on like slide 5 and then it doesn't get explained until slide 23, then you're lost for, the 18 slides or so. So I'd prefer not to do that. Okay, so brief, who am I? I am a kernel developer, co-maintain some subsystems. I've been working in the kernel for about 17 years through various companies, most notably for the length of time in Intel. My background primarily is in the network stack. So I've worked on the core stack, protocols, also the NetDev layer, implemented multi-queue support in the kernel many years ago, worked on device drivers, and specifically more importantly for this talk is the scalability of network devices. Let me see if I can turn on a little laser pointer thing. There we go. And so this scalability push is what was really got me into the world of IRQ balancing. So when we have devices that can generate massive amounts of I/O, you have lots and lots of cores in a system, it's really, really bad when all of those interrupts from all of those queues and everything fall on one CPU, right? That kind of defeats the whole purpose. So that was how I got into this. And then my day job, when I'm not out fighting crime with IRQ Balance, I do kernel and driver work in the high-frequency trading space at Jump. Okay, so long time ago, feels like a long time ago since pre-COVID, but at LCA 2019 in Christchurch, we had this presentation, talked about what IRQ Balance is, how it works, why it exists, and really what it kind of came down to was what are the real challenges that IRQ Balance has? And I'll have a couple more slides here in a bit trying to highlight some of the challenges. But namely, it's trying to take a bunch of disjoint information, so information about where is your card physically plugged in, like which NUMA node is it plugged into, so that means which PCI Express slot it's plugged into, to which CPU socket it's plugged into. That's one aspect. And then the other aspect is where is your application running? Which core is it on? Which NUMA node is it on? And then you have this pesky thing called a device driver that has an interrupt that's tied to a queue, and maybe you have multiple queues, and where are those interrupts pinned in terms of their affinity? And it's trying to take all of this disjoint information from the kernel that's exposed in various ways, and then trying to make a smart decision as to how to balance that interrupt. And then you have this other pesky thing of there are other devices in the system that also have interrupts, and they're also getting routed to CPUs. So it's really a very hard problem to solve to make everyone happy. And so usually anyone that has IRQ Balance running on their system knows they're not happy, and many oftentimes that they kill it, and then they run a script that manually affinitizes interrupts. But there are ways that we have actually extended IRQ Balance to try to solve some of that. And much of that detail is actually in that Christchurch implementation, namely policy scripts where you can actually inject some user control into IRQ Balance saying, I want to balance these interrupts myself. I know how they're supposed to be laid out, and then just do whatever you want with the other system level interrupts. So there is some flexibility there that we talked about. But the main focus has been on x86, right? So think multi-core systems that are like more enterprise, cloud, big workstations, lots of I/O, big network cards, 10, 25, 40, 100 gig cards. It was really found mostly in the x86 world, right? This is really the bread and butter there. And this last part, I want you to kind of file this one in the back of your mind. Interrupt discovery in terms of figuring out from the system at the PCI level, and even in some non-PCI level situations, has typically been through ACPI, right? So we can go and query, the device firmware through the PCI systems, and we can figure out where interrupts are, how many do we have. All of that is very standard and kind of auto-discoverable. And I noticed that my speaker notes here are super tiny. So I'm trying to think of what's coming up next without speaking to it before I actually get there. Okay. So let's try to recap some of those challenges that I kind of brought up. So I already mentioned that that there's all these unrelated sources. So one is C state and P state, so different processor state or different socket states in terms of power, right? One of the things that IRQ Balance tries to take into account is, did a certain CPU core drop into like a deeper C state? It wants to be turned off for whatever reason. You don't want to route an interrupt to that core because you're going to immediately wake it up. And if you're also concerned about performance, then you're going to have a latency hit waiting for that core to spin back up and blah, blah, blah. So we try to get that information out of sysfs and some of the CPU governor stuff for the scaling bits. CPU load, right? This is one of those, like, how do you measure CPU load? Is it wait time? Is it user time, system time? So we take some aspects of CPU load. How busy is this CPU? And also part of that is how many interrupts are actually firing on that particular core. I just figured out how to make this bigger. Excellent. So cache locality. This is something else that it tries to take into account, right? So if I am trying to balance out to a core, and if I'm on a system that has a certain hierarchy, say like an L1 is per CPU, and then an L2 is maybe shared across very tight cores, and then we have an LLC or an L3 cache, that I'm trying to land these things kind of in that same domain. So I have to take that topology into account as well. Numolocality. So if you are on a multi-socket system, you want to make sure that the interrupts for, say, like a NIC plugged into a network interface card plugged into a slot in NUMA node 0, you don't want to route all of its interrupts to NUMA node 1 unless you have a really, really darn good reason to do that. Now, so there's a new one. We'll talk about it a little bit more later. This is actually since 2019. There's a new thermal integration where we take some thermal characteristics and also make decisions based on, do we want to route an interrupt to a CPU that's overheating? The answer to that is no, we don't want to do that. So we try to steer interrupts towards or away from CPUs based on all of these above sources of information. Now, the problem is, one thing that I don't have up here, and it's still an issue, and I kind of alluded to it on one of the previous slides, is application level stuff. We have no insight into what the scheduler is doing, how it's dropping applications down on CPU cores. We have no idea what they're doing. So this is really like a best effort at the platform level to make it look like everything is happy and interrupts are firing in a spread out way. And if anyone, like I had mentioned, and I heard some laughs, so I have a feeling that people have run into this, that doesn't translate into that your applications actually work better when this is in play without any knowledge about what's going on. Okay, so I promised some crudely drawn pictures. So consider this. Let's see. This, two CPU systems, so two NUMA nodes. We'll say our first 4 physical CPUs are in one socket, the other are in the other socket. We have 2 DDR controllers. We have an I/O controller. We'll just call it PCI Express for now. Then we have a high-speed, super high-tech card down here. It has a physical PCI connection. And then I'm trying to illustrate, this is like worst-case scenario kind of thing. And this is what is like the bane of irqbalance, right? So I've got a NIC. I have a driver running on it in the kernel. And let's say the kernel driver happens to allocate memory for its data structures and its buffers, its DMA regions off of the other NUMA node. At this point, we've already lost, in terms of the performance battle, because every memory access is going to go across either the QPI or the Infinity Fabric, and that just sucks. So let's make it suck even more. So now I've got an application maybe running up on, CPU 1? In CPU 2. And maybe the interrupt for this is actually routed to CPU 1, and so the application is actually going to be woken up by CPU 1's interrupt, the exit of the interrupt. And then if the application has its memory mallocked off of NUMA node 0s, so you can see how this is starting to get very, very bad, right? This is bad. Don't do this. So ideally, what we're trying to do with irqbalance, and this is again where we don't have as much insight as we need to do some of these things, but this is ideally what we want. We have an application running on a CPU, let's say CPU 5. I have a NIC that is on that same NUMA node. It has its memory allocated from that NUMA node. I have an application that's also running its buffers on that NUMA node. This is all trying to keep memory bandwidth from having to burn QPI or Infinity Fabric, so Intel, AMD. Resources going between the CPUs, so your latency on memory accesses is lower. And then I want that same interrupt that is servicing the data coming out of the NIC to go to that same CPU that application is already running on. This is the ideal situation. You wanted a very vertical pillar because this also maintains cache locality, right? So that application's buffers are sitting in CPU 5's cache. You want to wake up that application and then not have to immediately take a cache miss, block, take the exception, page fault, swap it in, and then at that point, again, if you're worried about performance, then you've already lost. All right, does this sound reasonable? Everyone's still kind of awake? All right, good. I'm really glad that this wasn't after lunch, right after, because that's usually the food coma hits. So I know this is like edge of the seat topics here. So, all right, so what are some other things that are worth noting? irqbalance only balances hardware interrupts. Not software interrupts. So this is something that I think some people forget, and this was actually a question that Paul McKinney, who just spoke prior to this in a different room, Paul actually asked me this in Christchurch, and I thought about it, and I was like, crap, you're right. But IRQ balance does influence how soft IRQs can run, right? So one of the main uses for like heavy-duty software interrupt for data processing is in the networking context, or the networking core. So all of networking processing these days is done out of soft IRQ context. Basically, it's polling. It's known as NAPI. How many of you have heard of NAPI? Okay, good, good. So it's still known as the new API, even though it's, what, 18 years old. But it's effectively, we take a hardware interrupt, and this is where IRQ balance comes into play. We take a hardware interrupt on a particular CPU, and the NAPI model is to not do any work in the NIC in processing incoming queues, incoming data, and we immediately disable the interrupt on that CPU, and we enter soft IRQ polling with NAPI. And then the kernel goes ahead and decides when to start doling out work. Well, the CPU that we actually go into soft IRQ context is the CPU that soft IRQ interrupt will fire out of the kernel. So if we take the interrupt on CPU 5 and we go into NAPI context, the soft IRQs fire on CPU 5. But at that point, it's now out of IRQ balance's ability to migrate it to a different CPU. The only way is NAPI to not have any work to do, falls back in hardware interrupt context. We move things away to a different CPU, and then we start the process over again. Yeah, so I had already mentioned that IRQ balance isn't application aware to prevent bad decisions from being made. It tries to balance the system, right? So we're trying to balance between CPU load. We're trying to balance between, one CPU in particular isn't taking 10x the number of interrupts from other CPUs. So that's really its goal. And like I said, some applications performance can still suffer, and more often than not, they do. And then I had mentioned these policy scripts. This is a way that you can feed a script to IRQ balance. Has anyone used policy scripts in here? Even know what they are? It's actually not a terrible option to IRQ balance, but it is. So I'm sure that everyone has seen the venerable set IRQ affinity.sh script out there that you kill IRQ balance, then you run set IRQ affinity, and then set all of your interrupts. Well, this is basically taking that logic for set IRQ affinity, allowing you to generate a script in a certain format that you hand to IRQ balance and say, apply this when you're actually doing these other things, unless there are some certain things like thermal events or like CPU hot plug, then that you can't balance onto a socket that doesn't exist anymore. So I would encourage people to take a peek at that. Now, this is one other point that I want to make. And this is actually something I have contended and advocated for this for a number of years, this last point of letting drivers control their IRQ affinity. In fact, I had a patch set many, many years ago that was met with open arms and wonderful conversation. That was a pun. It was kind of dead in the water, and this is actually, if you have ever seen in looking at how IRQ balance works with the IRQ affinity hint exposed in proc, that was the alternative to this. The upstream maintainers said, no, you can't have a driver go ahead and set its own IRQ affinity. We don't want to expose that kind of policy level stuff in the kernel. IRQ balance should do it. So we went through and exposed a different thing in the interrupt core up to userspace, allowing a driver to say, I want this affinity to be this, give it a CPU map, and then IRQ balance decides to either use it or throw it away. I thought about this a long time, and I always contended that drivers had a better idea of where am I allocating my memory, from what NUMA nodes. I should have a better, I in terms of the driver, should have a better view on the world as to where I want these things to land. I don't think that's the case. I still think, I think these days that whether we balance in the driver or from IRQ balance, we're going to get the same result. Driver can still do a really good job of managing its own interrupts, but that can totally screw everything else on the system. So I'll go ahead and admit that that was probably not the right direction. So, okay. So what you're probably here to hear about is what are these two ISAs, and what is their role in kind of driving some of the irqbalance changes? So ARM and RISC-V, obviously ARM has been around for quite a long time, RISC-V as well, but it has certainly heated up quite a bit in the last few years in the Linux space itself. I've also got some links, I'll talk about them in a bit, on some talks from Drew Festini, who's very active. He's one of the RISC-V ambassadors. He's a good friend of mine. I've linked to a lot of the talks on RISC-V and Linux in general. So when we talk about some ARM and RISC-V SoCs, they do have similar challenges with irqbalance in terms of they themselves have similar challenges with irqbalance. So I wanted to make sure that I call this out just for the sake of less complexity in the slides, that each ISA has similar issues, but they're presented differently. And so specifically around interrupts, the way that an ARM system actually exposes interrupts through like the PPI, SGI, SPI type interrupts is very differently presented than the MCOS from the RISC-V side, but the net effect is the same, right? So they present things to the kernel implements them down in the system level, and how it discovers things through device tree, and then irqbalance then has the same view of the world, and it breaks in the same way on both of them. Surprise, surprise. So just if I'm saying like ARM, I mean ARM and RISC-V, right? Okay, so why haven't we seen these problems up until recently? Well, hobby boards have had typically really wimpy I/O, right? They didn't need to balance interrupts. Well, one, hobby boards either had SoCs that might have had one CPU, which I didn't call this out in this presentation, but recently we did have a patch come into irqbalance to support irqbalance on single CPU systems, which means more to detect that we're on a single CPU system and don't decide to run. So really, the hobby boards, the Raspberry Pis, the BeagleBones of the world really just didn't have anything compelling to worry about the interrupts from generating enough load that they actually caused a problem. Typically these things had like a 1 gigabit NIC, 1 gigabit Ethernet NIC, 1 gigabit NICs on those, like even the Realteks, very inexpensive ones, still had enough hardware offloads in the chip that they could do things like TCP segmentation offload or checksum offload, and it gave it plenty of offload capabilities for one single CPU core for like an ARM or a RISC-V to be able to drive gigabit. A lot of these 1 gigabit NICs were also hung off of like the USB bus internally, so there's no way you're ever going to get to 1 gigabit on these things anyways. So it just wasn't a problem. And then really the other things that people bought these boards for was all of these other GPIOs, the I2C, the SPI interfaces, and these either don't have an interrupt or you don't care about this interrupt. It's going to fire and you can get to it in milliseconds later and it's not going to be a big deal. Whereas like a 40 gig or 100 gig NIC, you got to get there in like, few microseconds at the latest before you overrun packet buffers. Okay, so no real need to balance interrupts. Well, enter today. Why are we here? These SoC boards are getting more interesting. Some of them, there was a recent one, it's actually an active discussion right now on the irqbalance mailing lists on some wireless routers that have some 10 gig ports. Well, 10 gig definitely needs more than one CPU, even in x86 to drive, at least on the receive side. So we're now getting into where we actually have to spread some load. New Wi-Fi protocols, Wi-Fi 5, Wi-Fi 6 are definitely causing issues. NVMe support, so high-speed disk traffic is coming in. We also have laptops, right? So people that have like an M1 or an M2 MacBook in the room or somewhere here that are running Linux, Linus famously runs Linux on a MacBook with an ARM chip, right? That has an NVMe disk, that has Wi-Fi 6, that has the ability through Thunderbolt to run 40 gigabits. So we are starting to see some things that are demanding that kind of load. And then the other aspect is the server side, right? So the server side has always been very disjoint, but with people like Ampere, Cavium with all of the ThunderX parts, Amazon with their Graviton, Ampere with Ultra. Just looked up, Ultra has 128 cores per socket. That's pretty dense. And you have a peripheral that's trying to load up all of those. I mean, if you have thousands of network queues attached to an Ultra with 128 cores and you dropped all the interrupts onto CPU 0, that really sucks, right? So this is something that we now have to take pretty seriously. Okay, so the architecture differences can be subtle, but they're enough to break things, right? The interrupt types are different from x86, right? So we have these PPIs, for example, the private peripheral interrupts. They get presented to Linux differently than, say, some of the other system-level interrupts in x86, and surprise, surprise, they don't get handled by irqbalance at all, or we handle them improperly. So this is another part, and this is where I said, file away the ACPI thing in your head. Device tree, and how device tree actually presents things, and how things can get named, and how they can actually get sorted into the tree, can cause a problem with layout or naming. Naming has actually been the bigger problem. Or some other BSP difference in how the blob is actually presented to the kernel. Device discovery is much different between ARM and RISC-V than it is in x86. And so in terms of the topologies and the trees and what is exposed to us to irqbalance from the kernel, it's very different. We also could have different platform drivers that just don't exist, right? There's the x86 platform drivers. There's the ARM platform drivers. They have their own class of stuff. So much more interesting stuff. What sorts of issues? And I'm just watching the time here. Okay, so these are actual issues that came up over the last few years. It's just a sample, but handling platform interrupts. So the architecture differences can be subtle, but they can be painful. And so this was the first kind of, I'll say, important fix. So this commit came in. So Hung actually works for Huawei, and I'll mention Hung a number of times here in this presentation, actually. So basically what happened was the PPI interrupts, these private peripheral interrupts in ARM, get presented to proc interrupts. Proc interrupts is the exposure of all of the interrupts and how they are laid out across the CPUs. That is one source of where we scrape information with irqbalance to see what is the kernel doing with interrupts, where are they at. And so what really ended up happening was, so here on x86 and kind of trimmed down, we have these system level interrupts that are per CPU, like local timer, IRQ work, et cetera, TLB shootdowns. These are interrupts that irqbalance ignores because these are per CPU. You don't screw with them. They just kind of hang out there. Well, in ARM, we have similar ones. These IPIs, interprocessor interrupts, these are PPIs. These are also things that we don't need to mess with the affinity. Well, irqbalance grabbed them, threw them into the IRQ balancing database and attempted to do stuff with it. And that was bad. So, it seems like a very simple thing, but it was something that we had never run into before because no one cared. And so someone all of a sudden had a board that they cared, and it became an issue. So we got a fix. That was great. Okay. Interrupt classification. This is one that I don't think is going to be put to bed yet. I think we're going to see more manifestations of this as more and more systems come online. But one of the things that irqbalance tries to do is, as it's going through and parsing all of the interrupt information and how interrupts are actually presented by devices, which there is no standard, right? So if I do request IRQ in the kernel and I give it an interrupt name, I could name it anything I want, more or less. But there are certain things that certain devices export certain interrupts in certain ways that irqbalance traditionally on x86 could figure out what exactly is this device and what kind of interrupt is it. So the types, so we have type legacy, we have MSI, MSIX, gigabit Ethernet. Yeah, we didn't plan ahead on that one. ETH, SCSI, which also covers ATA, serial ATA, NVMe. So again, we didn't really plan ahead on that one. Virtual event, so if it's like something interrupt firing off of like a virtual function routed to maybe to a virtual machine. And then the venerable IRQ other. We couldn't detect what it was. Well, see, maybe you can see where this is going. So we had another, actually this was, yes, this was also from Huawei. We had a fix to guess our ARM IRQ hints. And so what happened was we were going through and we were trying to match something. We matched it once, we went through the loop again, said we still don't know what this is, and then it got thrown into the IRQ other, and so it was getting handled like a system level interrupt and not an Ethernet level interrupt. So this was becoming a problem. And then we had another one that was very similar, and this one came in from TI. And so again, I think that you might be sensing a trend of companies that are actually like more and more interested in ARM SoCs, and they're getting bigger. So this one was basically another one where we were parsing some of the things and we weren't guessing the right class based on how they were being presented. So we got some fixes in for that, which took us to a third one. And this really goes to like the device tree level thing. We got foiled by a string. And this is not going to be limited to ARM or RISC-V. It just happened to be that we didn't run into this before in x86 because typically it's ACPI based. There's now device tree support, and there's more momentum behind that for supporting device tree on x86. So I suspect that we will see something like this. But something really simple and stupid as to the way that we parsed it out, there was an extra space, and so when irqbalance went looking for this platform driver, it couldn't find it because there was a space in the name. Or we parsed it out that way. So, oops. And then this is the last one I'll share, and this is a simple CI/CD issue where if we remember 2 slides ago, there was a fix to fix the guess check IRQ affinity, I'm sorry, get IRQ class, and try to classify the interrupts. The fix went in, and we happily merged it. And then we, shortly after, had a fix that says, hey, you broke everything else that's non-ARM. It won't even compile. So this really highlights like a platform issue, right, on the irqbalance side. This is now maintained by 3 people in our spare time. We don't have formal CI/CD to do pipeline builds and testing on multiple architectures. This is a gap. This is something that we need to address. So why all the issues all of a sudden, right? So arguably, irqbalance was kind of in maintenance mode. We were not really doing a lot with it. It just worked. I mean, for varying degrees of how you want to say it works, it worked. But really, the ARM stuff that was coming in, ARM was getting bigger. And this is something that I'll make this statement. I'm sure that I'll get some hate mail from it. But ARM has struggled, right, over the years with a fractured ecosystem. So slightly different CPU designs. Vendor A wants to put in, floating point. Vendor B wants to put in like this instruction. Vendor C wants to not put that instruction in. It's put an immense amount of pressure on the tool chains, right? So the compilers, if I'm using like a TI, BeagleBone, blah, blah, blah. Oh, did you get GCC version, blah, 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 dash, blah, 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 blah. Oh, no, you have the not blah, blah, blah. You have the other blah. Then, yeah, that's not going to work. So that's been something that has really hurt ARM over the years. And there's been a lot of improvements to fix this, right? I'm not saying that this is an unsolved issue, but also the BSP support, right? So you get a BSP to support a certain board, and everyone has a variant of a board, and then you have a different BSP blob for that, and the kernel has to deal with that. That's been a maintenance issue, right? So hobby boards have really, kind of made this a challenging issue. RISC-V is not immune to this. Yeah, so same vendor, different cores. Look at that, RISC-V not immune to this. I should remember what I wrote on the slides. So why all of a sudden did this become an issue? So server CPUs. So Ampere came in, Ampere hired a huge open source team. They're a great group of folks. I know quite a few of them. And one of their first jobs that they really wanted to focus on was cleaning up the ecosystem for ARM-based CPUs. Very, very big task. I think they've done a fantastic job helping shepherd that along. ARM desktop chips have become more powerful, and Yeah, so I mentioned this active thread around OpenWRT. This is actually the thing with the, got it, thank you. This is the thing with the 10 gig ports and Wi-Fi 6 issues. So what really happened is all of these things started showing up, and then they started running into problems with irqbalance because they kind of needed it to help the system level stuff, and they found out everything's broken. That's why this all of a sudden caused some renewed interest. So that's a really great thing. So one of the really nice things to come out of this was Hong Zhao from Huawei, who authored a number of those patches that I showed on previous slides, kind of came in and said, hey, between Neil Horman and myself, who co-maintain this, said, what do you think about having me as well? And we're like, that sounds great. Yeah, he's been very, very active. It's been a really nice addition because then this is also some really strong ARM expertise coming in and helping out with the direction of the project. And what ended up happening is as more and more people started like messing with this, and they're like, hey, there's this irqbalance UI thing too, and hey, I'll fire it up, and holy crap, it doesn't work, it breaks. So we got some patches. So as people were starting to come into this from the ARM and the RISC-V ecosystems, they started realizing that there was a lot of stuff that was wrong. And so all of a sudden this renewed interest started, and people started looking even deeper. We also added improved support for PCI hot plug. So if you hot plug a device, you want to remove the interrupts from the balancing database. That was something that wasn't there before. Thermal events. So this actually came in from Intel. So they actually hooked to ThermalD to basically feed information to irqbalance saying the CPU went offline because, or the CPU is having problems because of thermal issues, please route interrupts away. So the limitation here, and this is a call to action, is that this is only available on x86 64 right now. But not to fall back on Paul's thing before today, patches are welcome. But this is, I think, a good place that we could probably improve on in the ARM and RISC-V space. Okay, so looking to the future, what does the roadmap look like? irqbalance, I think, still has a lot of work to have better flexibility for device tree defined resources. Right, so this is something that has been baked into the irqbalance core. Is we can go through the ACPI mechanisms that are in the kernel, having something that we can actually hook into device tree and be a little bit more aware of how things are laid out. Because one thing that we have not run into yet, but I do fear this, is MSIX resources. So these are things that are typically dynamically allocated on a NIC or an NVMe drive on some kind of peripheral. These things get auto-discovered and then we try to bring them up. Well, if these things are actually tied to a device through a device tree, should we be balancing them? I don't know. So I guess time will tell. Yeah, the RISC-V platform interrupts that are similar to the ARM, PPI, SPI, SGI things, we need to comprehend that for RISC-V. CXL devices. So if any of you are familiar with Compute Express Link, it's a bus architecture thing that's basically on top of physical PCI Express. Just started showing up in Sapphire Rapids and AMD Genoa. There's a whole class of things, and I kind of also do a lot of stuff with the CXL consortium. So if you have no idea what type 1, type 2, type 3 devices in CXL are, see me outside. I'll be happy to give you a brain dump on CXL. But it's basically like an I/O, memory, and cache level protocol. We have no idea how to deal with that. And the ARM server proliferation. So Linux development, I mentioned that Drew Festini has a lot of talks on the state of RISC-V. They're just marching along really fast. I have a feeling that we're going to start seeing some like public server class RISC-V CPUs here not too long. It's probably going to put some pressure on irqbalance. So here's our GitHub project page. Please go ahead and feel free to poke around there. That's where the code lives. There is an old PR for CI/CD that just kind of rotted. We need to kind of resurrect that and get it going. Please feel free to contribute. Always happy to bring in some people. So recap, if you fell asleep. irqbalancing is still hard. It's hard to get it right. But ARM and RISC-V getting into the mix is really helping us out. We're back to pretty much active development, but we have a lot of work to do. And so just, I promise there are some links here in the presentation. They'll be posted later. But yeah, go ahead and put me on the spot and see if I can not answer something that you guys have. Appreciate your time.
Does anyone have any questions?
Oh boy, here we go.
Do you talk to the device tree people much about putting things in the device tree to help you know what the interrupts are?
Do we talk to the device tree people? No.
They love standardizing things these days, so I'm sure they'd love some more standardization. You know, if it'd help, it could go.
Absolutely.
The device tree used to be a lot better at being useful.
No, that's a
Putting
great idea. We haven't really thought about that, but that's a really great idea, especially with x86 now kind of getting more into the formal device tree area.
Yeah, can you talk about which that's server class chips?
So the question is if the x86 device tree stuff is server class chips. The short answer is yes, really for like appliance level stuff. So Red Hat is looking to add device tree support for x86 into RHEL 8 into pre-boot and all that stuff.
We had it for LPC.
Yeah, device tree did exist for like what's the Minnow board, x86 based hobby board, and AMD, yep. Other questions? I will be here all day today. I unfortunately have to go back to the States tomorrow, so if you need me, grab me wandering around, or contact me through whatever contact info is actually exposed on the site. So. All right, well, thank you for your time. Enjoy the rest of the conference.